Okay, we are going to talk about the central limit theorem with means to get this video started. All right, so the central limit theorem studies means of a sample, basically. Okay, if you collect samples of large enough data, then the sample mean will have normal shape. Okay, we need a sample size of at least 30. Okay, the larger the sample size, basically the better. Okay, all right, so the mean of a sample will equal the mean of the population. Okay, if a population has a certain mean, then the mean of the sample should pretty much be the same thing. Okay, the mean of the sample looks like this, the mean symbol, and then a little subscript here, we're going to have sample mean. Okay, so that's the mean of the sample, and it will equal the mean of the population. Okay. The standard deviation of a sample, that's a little bit different. What we're going to do is we're going to take the standard deviation and divide by the square root of the sample. Divide by the square root of the number in a sample. Okay, so the standard deviation of a sample mean, we're going to do standard deviation, and then it has the same little subscript, sample mean. So that's going to equal the standard deviation of a population, and we're going to divide by the square root of n. Okay, so this is an important formula, and the fact that those two things are the same, also important. Okay. All right, the z-score for a sample mean. So, you know, in last unit, we learned the z-score formula. Z was the mean, x minus the mean. Over standard deviation. Oops, standard deviation. Okay, now our z-score formula, when we have this type of data, a sample, with means, we're going to do the sample mean minus the population mean. We divide that by our standard deviation. So it looks slightly different. So this is what we did in the past. If we have an individual, if we have a sample mean, this is what we're using now. Okay, so these formulas are also important. Probably want to make sure they're on a cheat sheet if you're taking a test over this information. Important things there. Okay, the law of large numbers says that as a sample size increases, the mean of the results will get closer to the true expected average or probability. All right, so that says as your sample size increases, your number of trials, the people you're studying, you're going to get closer and closer to the expected true value. If you have a small sample size, it's not necessarily going to be close to the overall population average. Okay. All right, so let's do an example. So according to a report to the Portland Press Herald, the mean price of heating oil in December was $2.98 per gallon with a standard deviation of 35 cents. So this right here, our population mean is 2.98 and our population standard deviation is 0.35. Okay. All right, if samples of 37 heating oil prices were collected, what would you expect to be the mean of the sampling distribution of the means? Okay, so this is telling us n equals 37. Now this is looking for the mean of the sampling distributions. Okay, well, we were told before that it's the same thing as the mean of the population. Okay, so our answer to this question, as tricky as it's worded, is just 2.98. The same thing as the sample, excuse me, the same thing as the population mean. Okay. What would be the standard deviation of the sampling distribution? Okay, so now we're looking for this. And our formula above said take your population standard deviation and divide by the square root of n. So we're going to take 0.35 and divide by the square root of 37. These standard deviations are typically pretty small. All right, for this one, we get 0.0575. Okay, is the sample size large enough? Okay, well, here's our sample size, 37. The answer is yes, because it is bigger than 30. We need 30 in order for this math to work. It's bigger than 30. Okay, that's all you need. All right, so next, oh, still a question here. Okay, what is the probability that the price of a single gallon was less than $2.85? Okay, so if we're talking about a single gallon, then we will use the formula for Z that talks about an individual. Okay, so I scrolled up there for just a second. So this is like the old material. So I'm going to say that Z equals X minus the mean over the standard deviation. All right, so my X now is 285. All right, so I'm going to have 285 minus the mean, which was 298. And our standard deviation was 35 cents. All right, so when I subtract these, let me just double check my math here. Okay, so we will get negative 0.371. So I'm going to say my z-score is negative 0.37. And I want to know the probability of x being less than 2.85. So I'm finding the areas to the left of this particular z-score. All right, so let's do this. All right, so I need the z of negative 0.37. So all right, let me find my 7 column here. This one. Okay, so it looks like 0.3557 is going to be our answer here. Okay, now what is the probability that the mean of the samples? Okay, so since we have that keyword samples, now we're going to do the new formula for Z. So now we're going to do the sample mean. So 2.85 minus the population, 2.98. This time it's divided by our new standard deviation, okay, which you can do this one of 2 ways. I know from up here, my new standard deviation was 0.0575, so I can plug that in. Or I can do like 2.85 minus 2.98 divided by 0.35 over the square root of 37. Either one of those will get us the right thing. One thing I will say is don't round too much in this process. Hold on to at least 4 decimal places if you are going to do it this way. Okay, so either way, whatever route you take, you should get that Z equals a negative 2.26. Okay, we're going to use the same table for Z. So I'm going up here to my table. All right, and I need to find negative 2.26. All right, here's my 6's. So I'm going to say 0.0119. There's my answer. Okay. All right, so next question. All right, we have a population of values has a normally distributed mean with 155 and a standard deviation of 4.2. You intend to draw a random sample of 200. What is the mean of the sample distribution of the sample means? Well, this guy equals this guy, which equals 155. Standard deviation, this guy equals standard deviation over the square root of n. So I'm going to say 4.2 over the square root of 200, which is 0.29698. Okay, so if I need to answer this question to 2 decimal places, I would say 0.30. However, if I'm going to continue to work with this decimal in my problems, I'm going to hold on to at least 4 decimal places, if not 5. What is the shape of the sampling distribution means? It's going to be normally distributed. Okay. All right. So this question wants us to draw a bell curve. All right, our mean in the middle, this is still 155. But to find standard deviations away, now I'm going to add our new standard deviation. So this would be like 155.30, and then this would be like 155.60, and in this direction it would be like 154.70, and then 154.40. Excuse me. Okay. So that's all we need for that question. Okay. All right, next question. We have IQ scores. They're normally distributed. We have a mean, and we have a population standard deviation. Okay. What is the probability of a random person, so one person, having an IQ score less than 95? So this is our old formula for Z since it's one person. So we're going to say Z equals 95 minus 100 over 15. Okay, so this Z-score will be a negative 0.33. Okay, we need to find the area to the left of 33 since it says less than. Okay, so we're over here. I'm looking for a negative 0.33. Let me do this. All right, so it looks like I'm 0.3707. Yeah. Okay, next. Now we have our sample. So now this is the new stuff since we have our sample. So we're going to do 95 minus 100 over 15 over the square root of 50. Since we have 50 people, there's our n. Okay. All right. So this is, let's see here, negative 2.36. Let me just double check. All right. So really, this is Z-score. When you do it on our calculators, will give you negative 2.357. And we always round a Z-score to 2 decimal places. So that's why it's going to be negative 2.36 in our work. Okay. So I want to know the probability of X being less than 95. And this is really X mean. Okay. So we use the same table here. So now I need to do, let's see here, negative 2.36. All right, so I have negative 2.36. So I'm looking at 0.0, where am I? 0.0091, there we go. And there's my answer, okay. All right, same setup, we have 50 people in our sample. Okay, so what is the probability that their mean will be more than 105? Okay, so we're setting up Z, 105 minus 100 over the same denominator. Okay, this Z-score is going to be a positive 2.36. Okay, all right, so since the bell curve is symmetrical, let's think about this. If I have a Z-score of negative 2.36, I found that area to the left to be 0.0091. If I have a Z-score of positive 2.36, then that means this area to the right will also be the same area, 0.0091. Okay, so that's going to be my answer. Now, if you forget that, you can find the area to the left of positive 2.36. So let's do that. So it looks like it's 0.9909. All right, so the area to the left of positive 2.36, this area over here is 0.9909. So to find the area to the right, I would subtract, and I should get 0.0091. So either way, we're going to get that answer. Okay. All right, last question for this section. We still have 50 people. We want to know that the probability that their mean score is between 95 and 105. All right, so let's visualize what's happening here. I've got 105 and 92, not 95, excuse me. Okay. All right, so 105, we've done that problem already. This was a Z-score of 2.36. And this area to the right from our previous answer was 0.0091. Okay. I want to know the area between these things for my final answer. All right, I need a Z-score when we have 92. So let's do that first. 92 minus 100. All right, this Z-score is a negative 3.77. Okay, now when I go to look at my table over here, negative 3.77 is not on there. Okay, so when that happens, I'm going to assume the area to the left of this negative Z-score is 0. That means it's so far away from the mean that my picture here is not realistic. It's more like this, all the way over here. And we want to find the area between these two things. So we're going to assume the area to the left is 0, and this area is 0.0091. So I would have to do 1 minus 0 minus 0.0091 for my answer. So we get, excuse me, 0.9909. All right, there we go.